Welcome back, students. So, here when we ended here, the radius of the orbit of the hydrogen atom given as r is equals to 1 by 4 pi epsilon naught into e square by m v square. So, this is for the radius of the orbit of the hydrogen atom, that is electron, which is revolving at a distance, that is from this distance, that is the radius. So, from here to here, the distance of the orbit, right? So this orbit is a stable orbit, so that for the stable orbit, the electrostatic force Fe gives the centripetal force for the electron to revolve around the nucleus in a stable orbit, right? So for other atoms other than the hydrogen atoms, then the Z value is greater than 1. Right? So for hydrogen atom, the value of Z, that is atomic number of the hydrogen atom Z, that is equals to 1. Hence here in place of Ze, we written as 1 into E. Right? So for other than hydrogen atoms, the Z value is greater than 1. Then here we can put Z. Right? So for helium, for deuterium, the Z values is greater than 1, right? So r is the radius of the orbit of the hydrogen atom, and given the formula as r is equals to 1 by 4 pi epsilon naught into e square by m v square, right? So next, kinetic energy of the electron, right? So electron is revolving around the nucleus, means it has kinetic energy, right? So in the centripetal force, mv square by r means m is the mass of the electron and v is the velocity of the electron, right? So here where m is the mass of the electron and v is the velocity of the electron, right? So in the formula, where E is the charge of the electron and m is the mass of the electron and v is the velocity of the electron, which is revolving around the nucleus with velocity v. So it has velocity, means it has kinetic energy. So considering for the same, that is for the hydrogen atom, the kinetic energy of hydrogen atom, right? So as we know, the formula of kinetic energy K is equals to half m v square, right? So here we have the formula R is equals to 1 by 4 pi epsilon naught into e square by m v square. Now if you observe here, we have the value, that is m v square, right? So if we rearrange this formula in terms of m v square, then m v square is equals to 1 by 4 pi epsilon naught into e square divided by r, because this whole will shift to the LHS. m v square shift to the LHS, then it goes to the numerator. Then in the LHS r, it goes to the right side, then it goes to the denominator, right? So in place of m v square, we can write here, we can rearrange this formula. m v square is equals to 1 divided by 4 pi epsilon naught into e square divided by r, right? Now we can substitute here. So k is equals to 1 by 2 into, in place of m v square, that is 1 divided by 4 pi epsilon naught into e square divided by r, right? So if you multiply, then it becomes e square divided by 8 pi epsilon naught r. So this is the kinetic energy of the electron, right? So it has kinetic energy, then automatically it has potential energy, right? Potential energy of hydrogen atom, so that is U, right? So here we have the positive charge and here we have the negative charge. So from the electrostatic, we know the formula for the potential energy, that is electrostatic potential energy U is equals to 1 divided by 4 pi epsilon naught Q1 Q2 divided by R, where R is the distance between the two charges. So here the one charge is the nucleus and the another charge is the electron, right? From the electrostatic potential energy U, we have the formula 1 by 4 pi epsilon naught Q1 Q2 divided by R. So here Q1 is positive E value and Q2 is negative E value, right? So now by using the formula, the potential energy U is equals to 1 divided by 4 pi epsilon naught. Then here it is the positive charge, hence the Q1 is plus E, and for Q2 that is electron that has negative charge, that is minus E. Plus E into minus E divided by the distance between the nucleus and the electron is R, right? Here it is. So the potential energy U is equals to minus E square divided by 4 pi epsilon naught. So the potential energy is E square by 8 pi epsilon naught R, and the potential energy U is equals to minus E square divided by 4 pi epsilon naught R. Then the total energy, right? So the total energy of the electron in hydrogen atom, so total energy E, total energy E, that is equals to sum of kinetic energy plus potential energy, right? So the total energy E, total energy of the electron, that is equals to sum of kinetic energy plus potential energy, right? So here we have the kinetic energy value and here we have the potential energy value. Now substitute here, then we get the total energy E is equals to, so E square divided by 8 pi epsilon naught R plus of minus E square divided by 4 pi epsilon naught R, right? So now here if you observe E square by, we can take common E square by, here it is 8 pi, then from the 8 pi we can take 4 pi common, then 4 pi epsilon naught R, here also we can take common E square divided by 4 pi epsilon naught R, right? So E is equals to, we can take common E square divided by 4 pi epsilon naught R. So remaining is 1 by 2 minus 1. Now, if we simplify, half minus 1 is minus half. Then the total kinetic energy we get E is equals to, that is minus E square divided by 8 pi epsilon naught R. So this is the total energy of the electron which is revolving around the nucleus, right? This is the total energy, minus E square divided by 8 pi epsilon naught R. So here 1 by 2 minus 1, here LCM is 2, so 1 minus 2 divided by 2 minus 1 divided by 2. So minus 2 into 4, that is minus 8. Hence the total energy we are getting is E is equals to minus E square, where E is the charge of the electron and R is the radius of the orbit, right? So here we are getting the total energy is in negative, right? So that means the electron is bounded by the nucleus. So if you observe here, the total energy is negative. So this implies that this electron is bounded by the nucleus. So if we get the energy is positive, then this electron is not bounded with this nucleus, right? So this is separate from this nucleus. So this minus represents in the energy, that means the electron is bounded by the nucleus. So the negative energy, the minus symbol or the energy negative implies that is total energy of electron is negative, right? So the total energy of the electron is negative. So this implies electron is bounded by the nucleus, right? So this is about the electron orbit. So in the electron orbit, we find the orbit radius. So by using the orbit radius, we find the kinetic energy and we find the potential energy and total energy. So total energy we are getting negative. So this negative implies that this electron is bounded by the nucleus. That is, this electron is holding by this nucleus, right? So this is about the electron orbit. So in the main here, from the Rutherford theory, this nucleus is positively charged and electron is negatively charged. So these two are in opposite charges. Hence, from the Coulomb's electrostatic force, that is, we are getting the attractive force here. That is, attractive force between the nucleus and to that of the electron. So nucleus is heavier than that of the electron. So hence here this attractive force causes the centripetal force on the electron. So for that reason the electron is revolving around this nucleus with a velocity v and it has mass m, right? So hence the electrostatic attractive force is equals to the centripetal force. So equating those two values, then we get the orbital radius of the electron, right? So for hydrogen atom, the Z value is 1. Other than the hydrogen atom, the Z value is greater than 1, right? So from that we find the radius of the electron orbit and here kinetic energy, potential energy and the total energy. So from the total energy we conclude that the electron is bounded by this nucleus. If we get the energy is positive, then this electron is not bounded by the nucleus. That is, this nucleus will not hold this electron. So this is separate, went away from this nucleus, right? So this one is the conclusion of this total energy, right? So understand this one. If we get the positive here, then this electron will not follow the circular path. That is also one conclusion, right? So if we get the energy is positive, then the electron will not follow the circular path, right? So this is about the electron orbits. In the last class we discussed about the nucleus. So here we are finding the radius, that is the distance of the electron from the nucleus. That means the radius of this orbit, right? So next, drawbacks of Rutherford hypothesis, that is Rutherford model of atom, that is Rutherford atom model or planetary atom model or nuclear atom model. So here also we have few drawbacks or limitations. So the limitations of the Rutherford atom model. So in that first one is it could not explain the stability of the atom, right? So here also fails to explain the stability of atom. So this one is the first drawback, right? So it could not explain the stability of the atom, and the second one is it could not explain the line emission spectra caused by the hydrogen atom, right? So the second one is it could not explain the line spectra caused by hydrogen atom. So these are the drawbacks of the Rutherford atom model or planetary atom model. So Up to this, we studied two atom models. One is Thomson's atom model, and the second one is Rutherford atom model. Right? So the Rutherford main concept is he introduced the concept of the nucleus, and the electron is revolving around the nucleus. He also verified that by conducting the experiment, that is alpha scattering experiment, where alpha is the nucleus of the helium atom. So that charge is 2 times of the electrons. That is, it is positively charged and its charge is 2e. Right? So from this, here we find the radius of the electron and the energy of the electron. And few drawbacks of this atom model are: one is it fails to explain, or it should not explain, the stability of the atom, and it should not explain the line spectra which is caused by the hydrogen atom. So these are the drawbacks of the hydrogen atom. Right? So next topic we are discussing the spectra, that is atomic spectra. What are line spectra and atomic spectra? Right? So atomic spectra. So what are atomic spectra? That is spectrum. It consists of the number of wavelengths in a linearly arranged pattern. So that pattern we call as the spectrum. So here, what is atomic spectra? Right? So when an electric current is passed through a gas at low pressure, then the atomic gas will excite and it emits the radiations of certain wavelength. So that arranged in a pattern, then that we call as the line emission spectrum. Right? So when the electric current is passed through the gas which is maintained at the low pressure, right? So if we consider this one as the gas, right? So this one is the gas. For this gas, the electric current is passed, right? So here, what happens? These gas which are present in these atoms, these atoms which are present in this gas will excite. That is, atoms get excited and it emits the radiations. Right? So it emits the radiations of only the certain wavelength, that is lambda. So this type of spectrum, so if we observe these radiations in the spectrometer, then here we are getting the lines, right, like this. So this one we call as line emission spectrum, right? So what are atomic spectra means? The gas which contains the atoms when this gas is supplied by the electric current. So gas is maintained at low pressure, that is, gas is very cool, that is, maintained at low pressure means it is very cool. Then the electric current is passed through this gas, then the atoms which are present in this gas will get excited. So those excited atoms will emit the radiations. So these radiations will contain only certain number of the wavelength, right? So this, if we observe through the spectrometer, then we get the forms of the line. So that one we call as the line emission spectrum. Right? So understand this one. What are line emission spectrum? When a gas, that is when the electric current is passed through the gas which is maintained at the low pressure. So the atoms which are present in this gas will get excited. So these excited atoms will emit the radiations of only the certain wavelength. So those are called as the line emission spectrum, right? So this spectrum is what are line emission spectrum means? It consists of the bright lines in the dark background, right? So those are the light emission spectrum, right? So if we draw the spectrum here, so this one is the dark background. If you consider this one is the dark. So on this dark background, we are getting the bright lines. Hence, the name given as the light emission spectrum. So how we are getting those lines means those lines are the wavelengths of the emitted radiations from these atoms, right? So when these atoms or atom contain the gas which is subjected to the electric current, right? So these are the lines that are bright lines. So these are straight like this, right? So these are all straight lines. Right, so this one is the dark background and these blue color lines represent the bright. So this blue color represents the bright lines, right? So these are all straight. So here it is almost straight, right? So this one we call as the line emission spectrum. Right? So what are line emission spectrum means? Line emission spectrum is when the electric current is passed through a gas which is maintained at low pressure, then the atoms gets excited. That is, excited atoms emits the radiations of only certain wavelength. Not all the wavelengths, only certain wavelengths which are emitted by these atoms. Right? So if these will observe through the spectrometer, then we are getting the bright lines in the dark background. So this we call as this spectrum we call as the light emission spectrum. That is line emission spectrum, right? So here the blue color lines represents the bright lines, and in the back side here white space is there, right? So this white space represents the dark background. Right, so this is the light emission spectrum. So these have the wavelength, that is different wavelength. So here it is 91 nanometer, right? So the wavelength of these lines is about starts with the 91 nanometer, and here it is 122 nanometer. So from here to here, this wavelength group or this series we call as Lyman series. So this group of wavelength starts from 91 nanometer to 122 nanometer. Calling this group of wavelengths we call as the Lyman series, right? So next here 365 nanometer. 365 nanometer, and here the wavelength is 656 nanometer, right? So here starts from 365 nanometer. So all wavelengths are in nanometer. So that is nanometer. So here 656 nanometer. So this group of wavelength is called as Balmer series, right? So here the Balmer series starts from 365 nanometer to 656 nanometer. That is in the line emission spectrum. Next, here it is 820 nanometer, and here it is 1815 nanometer. So this line, right? So here starts from 820 nanometer and it ends at 1815 nanometer. So the whole here to here is the name given as Spectral Series, right? So this spectrum is classified into different number of series. So in that, the first one is the Lyman series, second one is the Balmer series, and third one is the Passion series. That is in the line emission spectrum. So this one is the line emission spectrum, right? So the line emission spectrum, the definition of the line emission spectrum is when the electric current is passing through the gas which is maintained at the low pressure, then the atoms are get excited and emits the radiations which contains the certain wavelengths. So these are the certain wavelengths, right? So these wavelengths, if we observe through the spectrometer, then we getting the bright lines, that is bright straight lines in a dark background. So that spectrum we call as the line emission spectrum, right? So this one is the first one, line emission spectrum, right? So next, when the white light is passed through this gas. So one more is the lines here. If you observe here, we have the closed pack of lines and few certain gaps between these wavelengths. So what it represents means it represents the structure of the element, right? So these lines and the spacing between these lines represents the structure of the atoms, sorry, structure of the elements, right? So the significance is the number of lines here, the how many number of lines. So these number of lines and the spacing between these lines represents the structure of the element. So no two spectrum have the same, that is no two spectrum has the same lines and same space between the two lines, right? So that means each element has different spectrum, right? So here the line emission spectrum, the number of lines, the number of lines and the spacing or and the position, otherwise we can say the spacing between the lines, or we can say the number of lines and their positions, or the characteristics of the elements. That is, it represents the structure of the element. That is, the number of the lines and the position of those lines, that is spacing between the lines, represents the characteristics of the elements, right? So if you consider one element, it has different spacing and different position of the lines compared to another element. So each element has different line emission spectrum, right? So no two elements, that is, no two elements has same spectrum, that is line emission spectrum. So these are the important points, right? So in this line emission spectrum, the position of the lines and the spacing between the lines gives the characteristics of the elements, right? So it represents the structure of the element, or it gives the characteristics of the element. So no two elements has the same spectrum. That means each element has different spectrum, that is different atomic spectrum, right? So that one is the atomic spectrum. So this one is the line emission spectrum, right? So next, when the white light is passed through this gas, right? So when white light is passed through this gas, then if we examine or if we observe the spectrum through the spectroscope, that is, if we observe the transmitted light, so when the white light is passed through this gas, so here what happens, the light will transmit through this gas, right? So when white light is passed through this gas, then the transmitted light is examined through the spectroscope, then we are observing the dark lines, that is dark space in the spectroscopy. That means the bright lines which are observed in the line emission spectrum, so those lines are appearing here in the black space, right? So in the dark space, that means the dark lines will appear in the bright background, right? So understand this one. So when the white light is passing through this gas, this transmitted gas, that is transmitted light, this one is the transmitted light. So when we examine or when we observe this transmitted light through the spectroscope, then we observe that the dark space will be observed in the spectrum. That means the emission, the line emission spectrum, we are getting the bright regions, so those regions we are observing here is the dark in pattern, right? So hence we call that one as absorption spectrum, right? So this one is the line emission spectrum. So in the absorption spectrum, whatever the bright lines which are observed in the line emission spectrum, so those lines which are observing here in the dark pattern in a bright background. So here we have the dark background for line emission spectrum. So in case of absorption spectrum, we have the bright background, so we are getting the dark lines, that is dark spaces wherever the bright lines which we appeared, so in the same places we are getting the dark patterns, right? So that one we call as the absorption spectrum. So simply if we rearrange here means, if it changes background, that is dark background, to the bright background, these bright lines will appear in the dark in color, right? So dark space will be appear. So this becomes the absorption spectrum. So when will we observe this absorption spectrum means when the white light is passing through the gas, right? So this transmitted light if we observe means the spectrum which we get it in the line emission spectrum. So those lines will be appear in dark in color when observed in a bright background, right? So that spectrum we call as the absorption spectrum. So this is about the line emission spectrum and absorption spectrum, right? So these are the series. So these series are called as spectral series, right? So the first spectral series was observed by the Balmer, right? So that will be in the visible region. So we have different spectral series, right? So these are all the spectral series. So in that first spectral series, as we already mentioned, that is Lyman series. Next, Balmer series. Third one is Paschen series. Next series is bracket series, and the last one is P fund series. So these are the five series which are observing in the line emission spectrum or in the atomic spectrum. So these series we call as the spectral series. So the first spectral series was observed by the Balmer in the visible region, that is this series. So this wavelength is observed by the Balmer in the visible light, right? So Balmer series is observed in visible light. So first time the Balmer series is, that is the series in the spectrum is observed by the Balmer, hence the name given as the Balmer series, right? So after that the Lyman, which is observed in the UV region, that is in the ultraviolet region in the spectrum. So next Paschen is infrared region, right? So the Paschen is in infrared, that is it is not exactly in the infrared, so that one we call as near to infrared region, right? So that one is the Paschen series. Next, the bracket series is in the mid infrared region. So next and the last is P fund series. So it is far infrared region, right? So these are the series which observed by the names as given like Lyman, Balmer, Paschen, bracket and P fund, and these are the visible regions where the spectral series are obtained, right? So in the UV region we are getting the Lyman series. The first time the series was observed by the Balmer, hence so they given name as Balmer series. Next Paschen, that is in the infrared region. Next bracket series in the mid infrared region, and the P fund series is far infrared region, right? So in the Balmer series he observed the pattern. So this pattern, that is absorption spectrum. So here we have the line emission spectrum. The absorption spectrum is first observed by the Balmer, right? So this one is the bright background. So this one is the bright background. So this one is the absorption spectrum of hydrogen atom. So this one is the absorption spectrum of the hydrogen atom. So here you are getting dark lines. So this one is the absorption spectrum, and here we have the line emission spectrum. So here we are getting the bright lines in the dark background, and in the absorption spectrum we are getting the dark pattern in the bright background, right? So here the Balmer observed, so and he given the names. So this one is H alpha, H beta, H gamma, H delta, and here it is H infinity, right? So the Balmer given the series for different wavelengths for the hydrogen atom. So this one is in the hydrogen atom, and this one is in the visible region, right? So he given the wavelength names, that is H alpha, H beta, H gamma, H delta, and H infinity. So after finding these wavelengths, so he given one empirical formula for finding the wavelength of these spectral lines. So that formula named as the empirical formula of the Balmer series. He given the formula for finding the wavelength of those lines of the spectral series, and he named that one as the empirical formula, and the formula is 1 by lambda, that is equals to R into 1 by 2 square minus 1 divided by n square, where n value is equals to 3, 4, like that, etc. Right? So this one is the formula first given by the Balmer to finding the lines, that is wavelength of the spectral series, where R is the Rydberg constant. So its value is, R value is 1.097 into 10 to the power of 7 per meter, right? So the value of the Rydberg constant is R is equals to 1.097 into 10 to the power of 7 per meter, and the formula is 1 by lambda is equals to R into 1 divided by 2 square minus 1 divided by n square. For n is equals to 3, right? So here we have the n value for n is equals to 3, then we get 1 by lambda, that is equals to R value is 1.097 into 10 to the power of 7, 1 divided by 2 square minus 1 divided by 3 square, right? So 1 divided by lambda, if we simplify the RHS, then we are getting the value 1.566 into 10 to the power of 6 per meter. Then we need the wavelength lambda. Then lambda is equals to 1 divided by 1.566 into 10 to the power of 6. So if we simplify, then we get 656.3 nano liter, right? So this one is the wavelength of the spectral line, and he given the name as H alpha for n is equals to 3. So here the value of this lambda is 653 nanometer, right? So if you observe here, we get that value in the line emission spectrum also. So if you observe here, so this one is the Balmer series, and the series ends with the wavelength 656 nanometer. So as this series is observed by the Balmer, he given the empirical formula to find the wavelength of the spectral line. For that formula, by using that formula, by putting the value n is equals to 3, we are getting H alpha. So this will be visible in red, right? So that is the red line, the wavelength of the red line, right? So this one is the wavelength of the H alpha. Now if we substitute n is equals to 2, then we get the value of H beta. Similarly, if we put the value of n is equals to 4, we get H beta. N is equals to 5, we get H gamma, right? So if we put n is equals to 6, we get H delta, right? So for n is equals to infinity, so this one is the least wavelength, right? So in home you try by putting n is equals to infinity, so 1 divided by infinity is 0, so 1.097 divided by 4. So if we simplify, we get the H infinity value, that is the least wavelength in the Balmer series, right? So that value is 364.3 nanometer when n value is infinity. So in between we are getting, here it is blue, and here we are getting the violet, and so on, right? So these are the wavelengths calculated by the Balmer. So first time he observed that in visible light, so hence the name given as the Balmer series, right? So this one is the empirical formula for the Balmer series. So this is the empirical formula for the Balmer series. So it is very important. In 5 marks they may ask for the numerical problem. If we remember the formula and the values of n, so values of n for Balmer series starts from 3. Similarly, they may ask for Lyman series, Pastel, right? So they ask any 2 wavelengths to calculate, either in Lyman series or in Balmer or any of these 5. So you have to remember this formula. That is 1 by lambda is equals to r into 1 by 2 square minus 1 by n square. So this one is very important. They ask for 5 marks, right? So if we similarly write the empirical formula for Lyman series, Pastel, bracket, and P-Fund series, right? So remember this one also. The Lyman series is observed in UV region, Balmer in visible, Pastel near infrared, bracket mid infrared, and P-Fund for infrared, right? So if we write the formula for Lyman series, that is empirical formula for Lyman series, one by lambda, that is equals to r into 1 by 1 square minus 1 divided by n square, right? So for Balmer we have 2. Similarly for Lyman we have n value is 1, right? So, sorry, n value starts from 2, 3, 4, and so on. So this is the formula for the Lyman series. So already here we have for Balmer series. So this one is the second one, and for the third For partial series, 1 by lambda, that is equals to r into 1 by 3 square minus 1 by n square. So if we remember the order, then we can easily write the formula for this series. So here n values varies from 4, 5, 6 and so on. Right? So next one is bracket series. So for the bracket series, it is 1 by lambda, that is equals to r into 1 by 4 square minus 1 divided by n square. So n values varies from 5, 6, 7 and so on. Right? So on the last one is P-fund series. For P-fund series, 1 by lambda, that is equals to r into 1 divided by 5 square minus 1 divided by n square. So here the n values varies from 6, 7 and so on. Right? So these are the formulas. Right? So if we know the order for Lyman, here the first value is 1, then n value varies starts from 2. Similarly for Balmer, this one is the second series. Here it starts from 2 and n value starts from 3. Similarly for Pastel, the series is third. So here we have 3 and n value varies from 4. And here for bracket series starts with 4 and n value starts with 5. And last P-fund series starts with 5 and n starts with 6 and so on. Right? So in general, if we write the formula in general, then we can write for Bauman series, 1 by lambda is equals to r into 1 by 2 square minus 1 divided by n square. As of now, we know nu is equals to c divided by lambda, then 1 by lambda is equals to nu divided by c. That is, frequency is equals to speed of light by wavelength, then 1 by lambda is equals to frequency by c. So 1 by lambda can be replaced by nu divided by c, that is equals to r into 1 by 2 square minus 1 by n square, and the frequency nu is equals to r into c into 1 divided by 2 square minus 1 divided by n square. So this is in terms of frequency. In the similar way, we can write for all the series. Just if we replace 2 by 3, then it becomes partial series. So next, if we replace 2 by 4, then it becomes bracket series. If we replace 2 by 5, then it becomes P-fund series. So this one is in terms of frequency, right? So this is also one important. If they ask for the frequency, then we use this formula, right? So this is all about the atomic spectra. So in atomic spectra, we have two types of spectrum. One is line emission spectrum and another one is absorption spectrum. So in line emission spectrum, the lines and their position will give the characteristics of the element. So no two elements have the same line emission spectrum, right? So absorption spectrum, we observe wherever the line emission spectrum, the wavelengths will appear, they appear in the dark form. So those called as the absorption spectrum, right? So we have the empirical formula. So on this formula we have problems, right? So in the next class we will discuss on that, right? Thank you.